Now we're going to learn the root test. The root test is similar to the ratio test, and it's really well suited for when you have terms that involve powers. I want to talk about that just a little bit more. It's really useful for when you have a series where everything, you have this big, thingamabob, it's a word, and it's all to like the k power or something like that. Or you have something like k to the k, or something like k to the 2k plus 1, stuff like that, where it's got the index in both the main line and also in a superscript. For all of those types, the root test tends to be the best one to use. Just a little hint. All right, so now how does the root test work? Well, actually, it works really similar to the ratio test. You have an infinite series, a sub k, or the sum of a sub k, and you let, I know it looks like a p, it's not. It's rho. This right here is rho. It's a Greek letter. Right? It looks like a p, but it's not. So rho is the limit as k goes to infinity of the kth root of a sub k, absolute value of a sub k, of course, because you can't take the kth root of a negative power for, well, all even values of k. So that would be equal to the limit as k goes to infinity. And we honestly don't write the root very often. We kind of write it at the first step because, of course, it's a sub k to the 1 over k power, because the kth root is the 1 over k power. That is what rho is. Now we interpret rho in the same way that we interpreted r. If it is less than 1, then the series will converge absolutely, and therefore converges, because convergent absolutely implies convergent. If rho is greater than 1, including if rho is infinity, then the series diverges. And if rho is equal to the 1, the test is inconclusive, and you'll have to go use a different test. Now remember from Calc 2, this is just a little review section. In Calc 2, not Calc 1, Calc 2, although maybe you did learn it in Calc 1, it depends, or Calc 1. Whenever you learned L'Hopital's rule, sometimes you've seen it twice. So Calc 1 or Calc 2, we learned that by L'Hopital's rule, that the limit as k goes to infinity of k to the 1 over k is equal to the limit as k goes to infinity of the kth root of k, same difference. Technically, it's of the absolute value, but whatever, we won't worry about that, which is equal to 1. This is true by L'Hopital's rule. It was proven back in that section. All right, that's just a little reminder, handy thing to know. Okay, so let's practice the root test now with a problem. So rho is equal to the limit as n goes to infinity of the nth root of the absolute value of negative 12 to the n over n. Okay, but nth root is not as useful to us, so I'm going to rewrite it as the 1 over n power. So it's absolute value of negative 12 to the n over n to the 1 over n power. All right. But remember, from pre-algebra, when you have a to the p to the 1 over q, that's a to the p over q, right, from algebra. So I can take this and make it n over n, and n over n is 1. So that would mean that it's the limit as n goes to infinity. I'm just going to kind of segment that off. And limit as n goes to infinity of negative 12, the absolute value, negative 12, n over n makes 1, so that's gone, and then n to the 1 over n. Okay, so, but that's the absolute value of negative 12 over 1. Because up above, we just said that n to the 1 over n would be equal to 1. So this is because of the above. let me just say it this way. Right? That above fact. I guess I should call this fact. Right? So we're going to use this fact a lot. Right? Okay, so because of that above fact, we know that that one's 1, and we know that this is just a constant, so it's the absolute value of negative 12, which the absolute value of negative 12 is 12. Therefore, rho is 12. Okay, rho is 12, which is greater than 1. Therefore, our series, which was negative 12 to the n over n, diverges, which is not entirely surprising. I mean, negative 12 to the n is exponential. An exponential is going to beat out a simple linear term any day of the week, right? So as we add, it's going to get kind of cray-cray, right? All right. Done with that. See, the root test is easy. Let's try it on the next one. All right. So you see what I mean? When you have a big old thing, big old fraction to the n power, that's what I meant when I wrote this part right here, right? A big old fraction to the kth power. That's what we're looking at. So it's a red flag. You want to use the root test. So this big old thing, fraction to the n power, use root test. Okay. All right. So let's do that. So rho is equal to the limit as n goes to infinity on this one of the nth root of this giant thing. So technically it's the absolute value, 5n minus 3n cubed over 7n cubed plus 2 to the n power. But that's the limit as n goes to infinity of 5n minus 3n cubed over 7n cubed plus 2 to the n to the 1 over n, right? So this nth root over here becomes this 1 over n power over here. Okay, but n times 1 over n, these are going to disappear. And so it's just going to leave you with the limit as n goes to infinity of, these will cancel, and it'll leave you 5n minus 3n cubed over 7n cubed plus 2. And then I'm not going to use L'Hopital's rule, but we know how this is going to go. There's a table in the notes that tells us that when we have a rational expression that we can just kind of finagle our way around it. It's essentially based on L'Hopital's rule, but we don't want to show L'Hopital's rule because you have to do it like 4 times to get the number. It was this table right here that said, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. So we're going to use that table from that section to kind of make it work. Technically, it's from 4.7 where this is derived from because it really comes from L'Hopital's rule, but we covered it in section 10.2. So we'll just kind of say that. L'Hopital's rule that's making it happen, but we're not going to sit here and do L'Hopital's rule 4 times. So it would be the absolute value of the ratio of the leading coefficients. And the leading coefficients are -3, because that's what the n cubed, and 7. So that'd be -3 divided by 7, which is 3/7. That's my rho value. Now notice that rho is less than 1. Therefore, I know that this must converge. There, going back a page, just to quickly note, if rho is less than 1, the series converges absolutely. 3/7 is less than 1. So rho, no, here, I guess I can just put this way. So rho is equal to 3/7 is less than 1. Therefore, our series, which was giant, let me see if I can fit all this in, 5n minus 3n cubed over 7n cubed plus 2 to the n converges. If you want, you can say converges absolutely, but converges absolutely implies that it converges.